This is the beginning of the last section, atomic and nuclear physics. We have to describe and give an example of artificial or induced transmutation. First point, this artificial or induced transmutation is not alpha, beta or gamma decay, because these occur naturally. Artificial transmutation does not. So, artificial transmutation is when a nuclear change is induced by, for example, firing a neutron at a nucleus. You fire a neutron at the nucleus, it will be absorbed and you change the nuclear structure. For example, the fissionable nucleus absorbs the neutron, then it becomes another isotope. Then it might be that that isotope is very unstable, and then that will split into two smaller nuclei. This is not a natural process. This is one that's been forced to happen. So we have a nucleus here, absorbs an incident neutron, becomes unstable and splits. It then releases, for example, 3 neutrons. So these split into 2 roughly equal sized nuclei, produces 3 neutrons, and these in turn produce another 3 fissions. This is a chain reaction. We have to construct and complete nuclear equations, and this is one you know of already, alpha decay. We know that we have a parent nuclide isotope decays into the daughter plus the particle, in this case the alpha particle. This we looked at in the last topic, so we need to write it this way, with the number atomic mass reducing by 4, and then we have 4 here. Here is an example of a fission, which is an artificial transmutation. A bit more complicated. First of all, we have uranium-235. We fire a neutron at it, and it basically transmutates into uranium-236. Notice that 92 is still the same number of protons, but we have one more neutron, so it becomes 236, another isotope. Then this isotope is unstable. This 236, or uranium-236, will then split into 2 roughly equal sized nuclei, 2 different elements, and also produce 3 neutrons. What we need to do is look at the total number of nucleons before and after the reaction. So we have 236 goes into barium-144 and krypton 89. You add them together, it becomes 233. So we're short of 3 neutrons. So 3 neutrons are produced here. What about the atomic numbers? 92 is equal to 56 plus 36. And that's true. So there are no neutrons produced. So this is an example of nuclear fission, where uranium-236 splits into these two products. What is the difference between fission and fusion? Which particles undergo fusion and which fission? A quick discussion. Fusion is when you get small particles come together, fuse together, make larger nuclei, and they release energy. Fission is the opposite. A large nucleus splits into smaller nuclei and releases energy. So fusion, small nuclei, smaller than Fe, join together, make a large nucleus, or a larger nuclei, and release energy. Fission, large nuclei split into smaller nuclei, and this also releases energy. Sometimes fusion releases energy, sometimes fission releases energy. Define the term unified atomic mass unit. This is the definition. It's 1/12 of the mass of an atom of carbon-12. So it's 1 atomic mass unit unified atomic mass unit. So an example could be 1 mole of carbon weighs 12 grams. What is the weight of 1/12 of one carbon atom? So we basically need to find out 12 grams divided by Avogadro's number, and then that gives us the weight of one carbon atom. Then we divide by 12 to find out what 1/12 is. And you can try that now. And one unified atomic mass unit will weigh 1.66 times 10 to the negative 27 kilograms. And here we have some other values. Carbon 12 weighs 12 unified atomic mass units. One unified atomic mass unit is the same mass as 931.5 MeV per c squared, and this strange unit we'll discuss soon. An electron has 0.0005485 unified atomic mass units, and it's equal to 0.511 MeV per c squared. This is a number you're going to see quite often. A proton has just more than one unified atomic mass unit, 938 MeV per c squared. A hydrogen atom has 1.007825 units. A neutron has 1.008665 unified atomic mass units. So you get an idea. Basically, the size of a proton and neutron, they basically have more or less the same mass. Now, nuclear synthesis. What happens when we have nuclear synthesis? Let's say we combine 2 protons and 2 neutrons, we find the total mass. The total is going to be the sum of the 2 protons and the sum of the 2 neutrons in unified atomic mass units, and we're going to end up with this value, which is basically 4.031882 unified atomic mass units. However, you weigh the mass of a helium nucleus, you're going to find it has a mass of 4.00156 unified atomic mass units. This shouldn't add up, this shouldn't work. We've made it from its constituent particles to have this amount, and yet really it has this amount. So the final mass is actually less than it should be. In putting these particles together, we find that they've added up to give a smaller mass. So this mass has disappeared, and we call this the mass defect. How is it possible that these 4 particles come together, and when they combine together, suddenly they weigh less? This mass defect is the difference of these 2 masses, the mass of the sum of the constituent particles and the mass of the helium nucleus afterwards, and we're short by this amount. Where did this mass go? Now this was understood by Einstein, and he was able to describe what happened, and it's called the mass-energy equivalence relationship, and it's the most famous equation in physics. The mass which has disappeared, the mass which has vanished, has turned into energy. He understood what was going on here, and he knew that this mass could be turned into a vast amount of energy. And when I say vast, E is equal to mc squared is the equation that we use. C is the speed of light. So speed of light, which is 3 times 10 to the 8 squared, is going to be 9 times 10 to the 16. So you get the mass defect, you multiply by a factor of 9 times 10 to the 16, and you will find out how much energy is going to be released by the fusion of those nuclides. So this is this mass-energy equivalence. Mass can be turned into energy. Energy can be turned into mass. They are equivalent This was a remarkable discovery at the beginning of the last century. Anyway, we're going to get on to convenient units. I showed you before some horrible units, but I'll just do an introduction to this now. We know that there are convenient units for energy sometimes. How much energy is used by a 2 kilowatt heater in 4 hours? Well, it's 4 times 3,600 times by 2 times by 1,000, and we end up with a very horrible number. Yeah, power times time, and it gives this horrible number, which is not convenient. However, we can derive a unit of energy which is from kilowatts and hours. We call it kilowatt hours. It makes it much easier. So 8 kilowatt hours is much more convenient than 28,800,000 joules. Another example that you've seen recently, we have to deal with convenient units of another unit is between energy and mass. You remember, when an electron is accelerated through 1 volt, how much energy does it gain? Well, conventionally, we know that the energy is equal to the potential difference times by the charge. So it's going to be, let's say, 1.1 times 10, 1.16 times by 10 to the minus 19 through 1 volt is 1.6 times 10 to the minus 19 joules. This is not a convenient unit, but we also know that we have an alternative unit where it's going to be the potential difference in volts times by the charge of 1 electron, which is E, and it's 1 electron volt. It's a much more convenient unit for us to use at this scale. So sometimes 1 electron volt is much more convenient unit to use when we're referring to very small unit quantities of energy. Now we're going to extend this to convenient units of mass. We know this equation is equal to mc squared. Let's rearrange to get in terms of mass, because we're looking for convenient units of mass. We can say mass is equal to E divided by c squared. And let's think of the convenient unit that we have for energy, for small amounts of energy. It's the electron volt. Energy is in electron volts, or kilo electron volts, or mega electron volts. So what we can do in defining mass, we can find the energy and just divide by c squared. So it's electron volts per c squared, or kilo electron volts per c squared, or mega electron volts c to the minus 2. So this is a convenient unit for mass. An example, the mass defect of helium we've worked out is 0.0304 units. 1 unit has a mass. We know that 1 unit has a mass of 931.5 MeV c to the minus 2. We're given this in the data booklet. So the mass defect of the helium is 0.0304 units, and each unit is 931.5 MeV c to the minus 2. So it makes the new mass defect 28.32 MeV to c to the minus 2. This is the amount of mass that is the mass defect. This is the amount of mass that disappears. So how much energy is released when helium is made from its constituent nucleons? We know that it's 28.32 MeV c to the minus 2 is the mass which is disappeared. It's turned into energy. We apply Newton's equation, E is equal to mc squared. And we know that m is the mass defect. It's going to be 28.32 MeV c to the minus 2 times by c squared. This is why this is such a convenient unit, because when we're using it in the Einstein's equation, we find that the c to the minus 2 cancels with the c squared. So we know we're going to have an energy that's released of 28.32 MeV. So that was in producing a helium nucleus, 4 nuclear particles joining together. So how much is released per nucleon if 28.32 MeV is released in producing the helium nucleus, and that's 4 nucleons, how much energy is released per nucleon? Just divide by 4. And we end up with helium having an energy released per nucleon of 7.1 MeV. In fact, most nuclei, when they're formed from their constituent nucleons, release around 8 MeV.